Hey guys. All right, so we're kind of in a little bit of a troubled spot right now. I my Surface Pen for whatever reason is not connecting anymore. So I have no way of actually writing any notes at the moment. And I have a backup pen. It is currently not working either. So I've got to figure this out today somehow. For the time being, what I'm going to do is I have the book pulled up. We'll just go over some of the notes from the book. I won't be able to leave this as a public video, but I can set it with a link on Canvas so that you can find it through there. Okay. All right. So we're looking at inverse trig functions, and this again, I'm just looking at the book here. All right. So just a quick recap of what we did on Tuesday. Remember that the a function, it only has an inverse if it passes the horizontal line test. So like we can see the sine curve and we see this axis, this horizontal line going through it. That means it's not one-to-one, so it doesn't have an inverse function. But if we leave it on a closed domain from negative pi over 2 to pi over 2 for the sine curve, now it passes the horizontal line test. So when I say sine inverse, that's what I mean. I mean sine inverse of x is y, if and only if sine of y equals x, and I'm on the range negative pi over 2 to pi over 2. And that way I can stay good with the horizontal line test for the sine value here, all right? So that means, again, sine inverse only gives me solutions from the fourth quadrant up through the first quadrant. Okay? All right, I got an idea. Let me, I think this will be a little easier to see if I put it up like this. Yeah, maybe not. Let's go back the other way. Yeah, sorry about that. Just trying to figure things out on the spot here. Okay, so what this means is that, again, sine inverse only has a range of negative pi over 2 to pi over 2. That's as far as it can go. Which means in its domain, well, think about the range of sine. The range of sine is only negative 1 to 1. So the domain of sine inverse really is negative 1 to 1. That's the only thing that makes sense. So if I plug in sine inverse of 5, you're going to get an error statement. All right, so we saw this example 1, sine inverse of 1/2. You just got to think, okay, when does sine equal 1/2? At pi over 6. Okay. Now, an interesting thing is, remember compositions of functions, if you compose two functions, they undo each other. So sine inverse of sine x simply becomes x. And here you do have to worry about domain and range issues, right? So I'm plugging x into the sine function, right? And so sine inverse can only give me angles from negative pi over 2 to pi over 2, and that's why we have this restriction, negative pi over 2 to pi over 2. And the opposite, negative 1 to 1, if I do sine composed of sine inverse. And these domain restrictions are a little technical. I mean, they're very technical. We don't have to worry about that all the time, but it is something just to keep in mind. All right, now, what I'm more interested in at the moment is finding something like the derivative of sine inverse. And it'll probably be something you're not expecting. Now, here's how we can do it. So we are going to do this logarithmic derivative, or like an implicit differentiation idea. It's similar to what we did with logarithmic derivatives. So watch this. I'm going to let y equal sine inverse of x. And I do want to keep in mind, so one more thing, keep in mind sine inverse, or your inverse trig functions are angles. Okay, so if you remember for trig, you plug in a angle, you get a fraction out of that. For inverse trig functions, you plug in a fraction and out comes the angle. So when I see sine inverse 1/2, my thought is I'm looking at an angle. Okay? So here, when I say y equals sine inverse of x, y is the angle. Y is the angle, because sine inverse x is an angle. And the relationship then is that sine y equals x. And so I know the derivative of sine. So from this, I can do some sort of implicit differentiation idea like this. So if I take the derivative of both sides of sine y equals x, with respect to x, the derivative of x is simply 1. The derivative of sine y, using implicit differentiation, would be the derivative of sine is cosine, so it's cosine y times the derivative of y, which is dy dx. So I get cosine y dy dx equals 1, which means dy dx equals 1 over cosine y, just solving it with algebra. All right. And now remember here, this is where some of the range and domain things come into play. If I'm talking about sine inverse, my angle can only come from negative pi over 2 to pi over 2, quadrants 4 and 1, which means cosine will always be positive over that interval. All right. And I can use the Pythagorean identity, sine squared plus cosine squared equals 1, and solve for cosine y and get positive the square root of 1 minus sine squared y. It's positive again because I'm coming from quadrants 4 and 1. And now sine squared y, remember sine y was x, so I can replace sine squared y with x squared. Okay, so that means then my dy dx, which is what I'm looking for, that's the derivative of sine inverse, can actually be written as 1 over the square root of 1 minus x squared. And because of the range, we have to limit our domain of x's negative 1 to 1, which makes sense in the denominator anyway, because if you plug something like, let's say you plug in 2 into the denominator, you get the square root of a negative, which we can't have. So this makes complete sense with what we had already. The derivative of sine inverse then is 1 over the square root of 1 minus x squared. And that's what we need to keep in mind. I hope that makes sense. If you have questions, please leave comments and I'll try to clear up what is unclear. Alright, so if we look at example 2 then, we have f of x equals sine inverse of x squared minus 1. And what we want to do is first figure out our domain. Then we want to look at the derivative and the derivatives domain. Okay, so remember for sine inverse, the domain, right, we're plugging in the fraction and getting out the angle. So if I plug in a fraction into sine inverse, that fraction has to be between negative 1 and 1 because that's the only thing sine can obtain, right? Sine can only go from negative 1 to 1. So the domain of my sine inverse function is negative 1 to 1. So that means the domain for the sine inverse of x squared minus 1, I have to restrict x squared minus 1 between negative 1 and 1, and that's what we're saying here. We're saying all the x's such that x squared minus 1 is bound between negative 1 and 1, which means x squared is between 0 and 2, and so that means the absolute value of x is less than the square root of 2 by taking the square root of all sides here. Or another way of saying that is from negative root 2 up to positive root 2, and that's what we have here in interval notation. Okay, I hope that makes sense. So there's our domain. Now, if I do the derivative of sine inverse x squared minus 1, we have to use chain rule. So first you take the derivative of sine inverse, which is 1 over square root of 1 minus u squared, here u being x squared minus 1. So notice we get 1 over the square root of 1 minus x squared quantity squared times then the derivative of what's inside, which would be 2x. So that's where I get this 2x times 1 over 1 minus, they just squared out this polynomial, and then finally combine like terms, and you get 2x over the square root of 2x squared minus x to the fourth. Okay. Now for part C, we're looking for the domain of f prime. And I think it's easiest to see that in this first expression, where we have the x squared minus 1 quantity squared in the denominator. We need all of this denominator to be positive, right? And 1 minus something is going to be negative if the something you're subtracting is bigger than 1. And we also can't have 0 in the denominator, so we need to make sure they're strict inequalities. So that's why we say the domain of f prime here is x squared minus 1 is between -1 and 1, just like we had at the top. Except in the part A, we can have or equals to, because we could get 0. Here, since I'm in the denominator, I can't have or equal to, because that would make the denominator 0. And so we get a similar calculation, except this time we're not allowed to have 0. So instead of going from strictly negative root 2 to root 2, I have to say negative root 2 to 0, neither included, and 0 to root 2, neither one of them included. Okay, I hope that makes sense. Let me know if it doesn't, okay? All right, now moving on to cosine inverse, we can do a similar thing. But if you remember, so this graph, these two graphs are great. Look, cosine x goes from positive 1 down to negative 1 if I go from 0 to pi. If I had started at negative pi over 2 like we did with sine, it would not pass the horizontal line test. So cosine inverse is a little different. We just go from 0 to pi. 0 to pi. All right, and here's a graph of cosine inverse, or remember another way of saying that is arc cosine. We're going from -1 to 1, starting at pi, going all the way down to 0, okay? And this makes it clear then that the range of cosine inverse, the domain of cosine inverse, just like sine inverse, is -1 to 1, right? It's the same deal. Okay, now we have these composition rules again, and I'm not going to worry too much about that. And if I do the exact same expression, let's go back up to when we calculated the derivative of sine inverse. If I do this exact same thing except with cosine inverse, the only thing that changes is the derivative of cosine y, would be negative sine y. Negative sine y. And so for that reason, you follow the rest of the calculations the same way. Your derivative of cosine inverse is negative 1 over square root of 1 minus x squared. So it's a very similar calculation. It's just you get a negative instead. So there is the derivative of cosine inverse. Okay, closely related to sine inverse, maybe more so than you even realized. Okay, let's move on then to something a little bit more interesting, and that's tan inverse or arc tan. All right, so here we have tan inverse of x as y, and remember tangent is negative in quadrant 4, positive in quadrant 1. So just like we did with sine, like here's the graph, and notice you have these vertical asymptotes at pi over 2, and you have this nice curve. It almost looks polynomial except for the asymptotes, right? We limit then tan inverse just to negative pi over 2 to pi over 2. Its range is negative pi over 2 to pi over 2. Okay, just like we would do with sine. Okay, so let me skip example 3. I'll come back to it. I want to show you the graph. Here's the graph of tan inverse. And so notice it's like when you graph an inverse function, you just put the line y equals x, and you do a reflection about that line. And so if you did a reflection about the line y equals x with tan inverse, you get this line. You get this curve. So instead of vertical asymptotes at pi over 2 and negative pi over 2, you have horizontal asymptotes at those same positions. Okay? And so notice here, my domain for arctan, it's not limited to -1 to 1. Tangent can actually obtain any value, right? Look at the graph. Tangent can go from negative infinity to positive infinity in its range. So the domain of tan inverse is negative infinity to positive infinity, which is very interesting. Okay, so that's why we say here the limit of tan as I approach the asymptote pi over 2 from the left goes to infinity. All it's saying is, look, if I go towards pi over 2 from the left, I'm going to go up to infinity. And if I go to negative pi over 2 from the right, I go down to negative infinity. That's what we're saying right here. So if I want to look at this graph tan inverse, and I want to say what's the limit as I go to positive infinity, well, it's going to be that horizontal asymptote at pi over 2. and going to negative infinity, horizontal asymptote at negative pi over 2. Make sense? Okay. Let me go back to example 3. We're going to simplify this expression now. I have cosine of tan inverse of x. And it's good practice to kind of get an idea of how to do this. And when we take the derivative of tangent, you'll see how relating the trig to the algebra is actually a very powerful tool. All right, so here we have y equals tan inverse x. And so I'm going to let then, just like we did with sine and cosine earlier, I'm going to let x be tangent y. And I'm restricting that y from negative pi over 2 to pi over 2, again to be consistent with passing the horizontal line test. Okay. Now we want to find cosine y, but since we know tangent y, let's see, what identity can relate tangent and cosine? Maybe the quotient identity, but that also involves a sine. I think it's going to get more complicated that way. Instead, why don't we use the Pythagorean identity that relates tangent to secant, and then from there we can go from secant to cosine. And that's our strategy here. So what I'm going to do, and I hope that makes sense what I'm saying. Look, if y is tan inverse x, remember tan inverse is an angle. So what am I trying to find? I'm trying to find cosine y. That's the goal. So how do we do that? Well, there's a couple ways. In the first way, we're going to use identities by this method. I know secant y can be related to tangent y through the Pythagorean identity. Secant squared theta equals 1 plus tangent squared theta. So here secant squared y equals 1 plus tangent squared y. And now I'm going to replace tangent y with a value of x, because remember tangent y is x. So secant squared is actually 1 plus x squared. So then secant y is the square root of 1 plus x squared. And I don't have to worry about the negative, again, because, and what I mean by that is, remember when you take the square root of both sides, you're supposed to say plus or minus. But remember secant y is positive because, we're restricting our y values from negative pi over 2 to pi over 2. Quadrant 4 and 1, cosine and secant are both positive on those quadrants. So this is fine, the square root of 1 plus x squared. So that means that's secant y. Cosine y is a reciprocal of this. So cosine of tan inverse x, maybe an easier way of saying that is cosine of y, because remember y is tan inverse of x, is a reciprocal of secant y, which gives me this 1 over the square root of 1 plus x squared. So this cosine tan inverse x, actually, it's weird, right? We're dealing with a trig and an inverse trig function, but they reduce to more of an algebraic statement. 1 over the square root of 1 plus x squared. And that's what the value of analyzing things in this manner is. All right, so another way of doing it, if you don't want to use identities, we can use a triangle. So here again, we're letting y equal tan inverse x. And you'll want to keep this in mind. We're going to do a similar thing in chapter 7, if we can get to it, hopefully. Looking at this, an expression like this. So we have y is tan inverse x, which means tangent y is x. So from that, I'm going to draw a triangle. And my angle is y, so that's why I have the y here. And tangent, remember the definition of tangent is opposite over adjacent. So in this triangle, I know if that's y and tangent y equals x, then the opposite side and the adjacent side have to have the fraction opposite over adjacent has to be x. So I get x over 1. X and 1 are the other two sides of my triangle. Okay, does that make sense? Let me say that again. Tangent y equals x. Y is my angle. Tangent is opposite over adjacent. So my opposite side's x. My adjacent side's 1. X over 1 equals x. Tangent y equals x here. From there, I can use the Pythagorean identity, or the Pythagorean theorem, sorry, to solve for the third side. X squared plus 1 squared equals the hypotenuse squared. So you take the square root of that to get the hypotenuse to be square root of 1 plus x squared. So then cosine of y, which again is cosine of tan inverse. Cosine is what? adjacent over hypotenuse. That's going to be adjacent side over the hypotenuse, 1 over the square root of 1 plus x squared. That's a really cool idea. I really like that idea. I hope that makes sense to you, drawing the triangle and engineering it that way. It's a good idea. It's a good strategy. Okay, now I wanted to do example 4 before I did example 3, and I just kind of got lost in the discussion. But let's go back to this limit idea real quick. Okay, so remember, for tan inverse, as I'm going out to infinity, I'm approaching this horizontal asymptote at pi over 2, and out towards a negative infinity, I'm approaching a horizontal asymptote at negative pi over 2, right? So if I have arctan of 1 over x minus 2 as x approaches 2 to the right, can I begin to evaluate something like that? That's a good question. We're not approaching infinity here, or my x is not approaching infinity. Do I have any hope of doing this? Okay, so I'm going to take what's in the middle and relabel that as a variable. I'm letting t be this 1 over x minus 2. Now we have to think way back to Cal 1. What do these graphs look like, this 1 over x minus 2? If you remember, it has a, well, why don't we pull up Wolfram Cloud, and I'll show you real quick. Just go here. All right, so we want to plot 1 over x minus 2. Let's let x go from, all we need to include is the 2 to see what we want to talk about. All right, so look, there's my graph of 1 over x minus 2. And notice we have a vertical asymptote here at 2. And if I'm approaching 2 from the right, so if I'm going to 2 from this direction, what is happening? Imagine if you're on this roller coaster, if I'm going to 2 from the right, I'm going up to positive infinity. Can you visualize that? The way we said this in Cal 1 is we said if the limit of 1 over x minus a approaching a from the right, we go to positive infinity, just like this. If you're approaching a from the left, you're going to negative infinity, like that. Okay, and it's probably been a while since you thought of that. Every once in a while we'll need to bring it up. Okay, so now, looking back at this, if t is 1 over x minus 2, then as x approaches 2 from the right, what did we just see? You have a vertical asymptote, and your graph is going up like this. Okay? As x is approaching 2 from the right, this function t is going to infinity. So I could rewrite this limit instead of x's in terms of t. The limit as t approaches 2 from the right of arctan of 1 over x minus 2 is actually the same thing as the limit as t approaches infinity of arctan t, which is that horizontal asymptote at pi over 2. Make sense? Yeah, hopefully. All right, just let me know if it doesn't. Okay, so now we're ready for the tangent derivative, tan inverse derivative, and we're going to do it the same way we did the others. So here we're going to let y equal tan x, which means tan y equals x. And now I'm going to do implicit differentiation, take the derivative of both sides. So the derivative of tangent y is what? Secant squared y, secant y squared, so we should say secant squared y, times the derivative of what's inside, which is dy dx. The derivative of x is just 1. So then I get dy dx is 1 over secant y, or secant squared y. Okay. And then from there, I need to get it back to x's. So the way I have to do that is by using tangent. And so I'm going to rewrite secant squared using the Pythagorean identity. 1 plus tangent squared y equals secant squared y. And then from there I can replace tangent squared with x squared. So the derivative of tan inverse is 1 over 1 plus x squared. That is very valuable. I told you already about my my calculus teacher who just constantly drilled that into us. But this is a very useful derivative. In particular, think in a little bit we're going to do integrals. The integral of 1 over 1 plus x squared dx is something we couldn't do until today. The integral of that is tan inverse x. And you could think, well, if there's no x in the numerator, you can't use a u substitution. So it'd have to be something other than what we've done already, and that's tan inverse. All right, now the other three, the reciprocal inverse trigs, so cosecant, secant, and cotangent inverse, they follow a very similar pattern. We don't spend a long time on them, so I never make people memorize this. You have to be careful on your ranges and your domains. They're a little different than what we had. I'm not going to spend a long time on that, okay? But they're here for you in case you need them, be able to reference them. But what we will need to know is the derivatives of our inverse trig functions. And I will include the cosecant, secant, and cotangent inverse in that discussion, okay? But notice that they are all very similar. So we already did the first three. Sine inverse derivative is 1 over 1 minus. It's 1 over the square root of 1 minus x squared. The cosine inverse derivative is negative that. And then tangent inverse is 1 over 1 plus x squared. Now, from there, notice the cofunction relationship. So tangent and cotangent derivative, I should say tangent inverse and cotangent inverse derivative are the same thing, except the cotangent one's negative. Same with sine and cosine inverse. Same with arc cosecant and arc secant. Arc secant is 1 over x, the square root of x squared minus 1. Arc cosecant is negative that. Okay, so the pairing is with these cofunctions. Okay, so remember, if you remember three of them, if you remember sine inverse, secant inverse, and tangent inverse, you know all six of them. Okay, that's the rule. All right, so let's practice this a little bit, and then we'll get into some integration. Okay, so let's example 5. Let's take the derivative of 1 over sine inverse. Okay, so we're going to have to use some chain rule here, because remember sine inverse to the negative 1 power. So when I take the derivative, first you take the derivative of what's inside, so that's going to be negative sine inverse to the negative 2 power. And then you multiply that by the derivative of what's inside. So the derivative of what is inside, sine inverse x. So now when I take its derivative, I get the negative 1 over sine inverse x squared, right? Because that was x to the negative 2, sine inverse x to the negative 2 power. The derivative of sine inverse, again, is 1 over the square root of 1 minus x squared. So that's where we get this expression here. That's its derivative. It's not pretty, but there it is. All right, so for b part, if I have x arctan square root of x, when I take its derivative, I'm going to have to use what? Product rule, because I have two functions multiplied together. So by doing that, I get the derivative, I get first, which is x, the derivative of the second, which I'll have to use chain rule. What's the derivative of arctan? 1 over 1 plus u squared. So I get 1 over 1 plus u, which is root x quantity squared, times the derivative of u, which would be the derivative square root of x, 1 half x to the negative 1 half power, right? Remember that, because square root of x is x to the 1 half power. Okay, so that's first d2 plus the second, which is arctan root x, times the derivative of the first, which is 1. All right, now cleaning this up. So notice here I have the square root of x squared, which is x. The 1 half, I can just bring a 2 down in the denominator. And how did I end up with the square root of x here? I really wish I had my pen. But remember, this is x. X to the first power is the same thing as x to the 2 halves power. If you multiply x to the 2 halves times x to the negative 1 half, you add their exponents, which gives you x to the positive 1 half power. And so that's why I have the square root of x in the numerator. Make sense? I hope so. Okay, let's go on then to example 6. And this is an interesting one because it's not something that in a calculus class, we don't try to do a lot of proving. But here, did you know that tan inverse x plus cotangent inverse x always equals pi over 2? You may not have known that, okay? But if you add arctan and arc cotan, you always get pi over 2. So how do we figure that out? Now, you could do this using trigonometry, but let's take a calculus approach, which I think is pretty slick. So what we're going to do is we're going to define a function, f of x, to be tan inverse plus cotangent inverse, okay? Then when I take the derivative of that function, watch what happens. The derivative of tangent inverse is 1 over 1 plus x squared. The derivative of cotangent inverse is negative 1 over 1 plus x squared. Remember that? Because I have that cofunction relationship. So when I add these two together, the derivative is a 0. All right, so what kind of functions have derivatives 0? Well, for example, f of x equals 3 has derivative 0 because the derivative of any constant is a 0. And so since my f prime is always 0, I know f of x is going to be a constant. Now we just have to figure out what that constant is. So the way you could do that is pick any input you want for x to plug in f and see what you get, because you're going to get the same answer regardless of x. Okay, does that make sense? Because because the function is a constant. So the one the book picks, which I think is a good choice, let's pick 1 because that's something I know with tangent pretty quickly. I know that if I have 1 in tan inverse, again I'm thinking what angle, tangent of that angle is 1? Pi over 4. Same for cotangent. Cotangent inverse of 1, what angle, cotangent of that angle is 1? Pi over 4. So I get pi over 4 plus pi over 4, and I get pi over 2. And therefore, what we wanted to prove, arctan x plus arccotan x, is pi over 2. That's pretty slick. I really like that. That's pretty neat. Okay, let's turn to integration. Now, the most valuable expressions here with integration are sine inverse and tangent inverse because, the secant inverse probably somewhere is useful, but the others are just negative versions of those. So here, look, if I had the integral of 1 over the square root of 1 minus x squared, try to use a technique that you've already used. Try to use a u substitution or something. It's not going to work. It doesn't work here. So what I use is the fact that the antiderivative of 1 over square root of 1 minus x squared is sine inverse x, plus the constant c, of course. And for tangent, the integral of 1 over x squared plus 1 equals tan inverse plus c. These are extremely valuable. Keep them away. File them away. If you're going to take differential equations, you're going to see this again. Okay, this is a useful thing. And it'll surprise you when it shows up. All right, so example 7. I want to integrate 0 to 1/4, 1 over the square root of 1 minus 4x squared. We try u substitution first. U equals 1 minus 4x squared. Du then would be negative 8x dx. There's no way I can apply u substitution here because I don't have an x in the numerator. If I had an x in the numerator, u substitution would work. If I don't, I'm going to have to do inverse sine. Okay, so what I'm going to do here is I'm going to recognize, the 4x squared kind of messes this up, right? We only have 1x squared up here. That's not a big deal though, because I can recognize that 4x squared is the same thing as 2x, quantity squared, and now I'm going to use a u substitution, let u be 2x. Okay, so if u is 2x, then du is going to be 2dx, right? So that means I have 1/2 du. dx is 1/2 du. I also can do a table to change my limits. When x is 0, u is 0, and when x is 1/4, u is 1/2, right? just by plugging in a u equals 2x. So then my integral becomes, let's see if we did this right. The integral, our original integral is going to be, let's see, we had 1/2 du, so take the 1/2 out. I'm integrating from 0 to 1/2 du over 1 minus square root of 1 minus u squared, because u was 2x, and I had 1 over square root of 1 minus 2x quantity squared. Make sense? From there, I'm just ready to recognize that that is sine inverse u. So I have 1/2 sine inverse u going from 0 to 1/2. So I plug in 1/2 and 0 here. And I got to remember what angle gives me 1/2 for sine? Pi over 6. How about 0? Sine of 0 is 0. So that's 0. So I have 1/2 times pi over 6 minus 0, which gives me pi over 12. That's how I get that. Make sense? I hope so. All right, example 8. We are going to derive this formula here. The integral of 1 over x squared plus a squared dx, so this is a more general version of the tan inverse integral, is 1 over a tan inverse x over a plus c. How on earth do you get that? Good question. I'll show you. All right, so in example 8 here, we have the integral of 1 over x squared plus a squared dx. And what I'm going to do is a clever algebra technique. So to do the tan inverse integral, I need this constant down in the denominator to be 1, not a or 3 or whatever it is. It has to be 1 in order to do this. So what can I do? That I have an a squared here. Well, let's factor out a squared out of everything in the denominator. See how I did that? I took out an a squared, which leaves me now with a plus 1 over here. What it does for the x squared, though, is it becomes x squared over a squared. And if that's confusing, distribute the a squared back across and see what you get. When I distribute a squared across x squared over a squared, I get simply x squared. Okay? So what I can do then is factor out the a squared as 1 over a squared here. And now I have the integral of dx over x over a quantity squared plus 1. And that looks worse than what we started with, except now I'm allowed to do a u substitution. U is x over a. Okay, and notice, remember a is a constant, so the derivative of x over a is just 1 over a. And I don't quite have that. I have a du. dx is a times du, just solving this for dx. And so then I have, let's go over it again. The integral of dx x squared over plus a squared is going to be 1 over a squared a du over the integral u squared plus 1. I can factor out the a to get 1 over a. Integral of du over u squared plus 1. Now I'm allowed to integrate that. That's going to be 1 over a arctan u plus constant c. And finally, we get the formula we wanted. We replace u back with x over a. And so the way to integrate x squared plus a squared, 1 over x squared plus a squared dx, is like this. Very cool. Very cool. So let's look at example 9 and let's figure this out. We're going to have to use this formula to do it. All right, so here I have x over x to the fourth plus 9 dx. All right, so since there's an x in the numerator, I think first thing we would probably try is to let u be x to the fourth plus 9. If u is x to the fourth plus 9, du then is what? 4x cubed? And that's not going to work because I don't have an x cubed, I only have 1x. All right, so what can I do? Wait a minute. X to the fourth is the same thing as x squared quantity squared, right? So if I let u be x squared, then this x to the fourth can be replaced with u squared. And notice, if u is x squared, du is 2x dx. And I do have an x up there. And so what I'm going to do is apply that. I'm going to have 1 half x, I'm sorry, 1 half du. And I'm going to let a, from my formula up here, be, well, I had a squared is 9, so a has to be 3. So then this is what I have. I have the integral of x squared over x fourth plus 9 dx is 1 half, that comes from solving for dx, du over u squared plus 9. U squared plus 9 in the denominator, I can apply my formula. That integral is going to be 1/3 arctan u over 3 plus c, and that is times 1 half, don't forget. So then I end up with, going back, u is what, x squared? I get 1/6, because 1 half times a third, 1/6 tan inverse x squared over 3 plus c. There it is. That is awesome. Okay, guys, this is 6.6. I basically just read you the textbook. I don't know if you've seen, there are a lot of celebrities like reading children's books online. So that's kind of my version of that. I'm not a celebrity, and this is not a children's book, but I'm just reading you a book online. Hopefully, I can get my pen going. I really need that for the rest of my classes. So that's going to be the fight I have today. Let me know if you have any questions. I'd be glad to help. And I hope you're doing well. And I'll see you later. Take care.